Hello colleagues, my name is Phoenix and this is the 8th episode of my SKSE modding tutorial series. In this video, I will explain how to modify game's assembly code with your own. To understand this video and successfully engage in reverse engineering, you need basic knowledge of assembly language. I won't explain the fundamentals as there's plenty of information available online. For example, I found a good playlist that might help you. I haven't watched it entirely, but the first few videos and the topics of the others seems useful. You actually don't need to follow the actions by the author, especially running your programs in assembly. Also, knowledge of SIMD won't necessary for now, so those videos can be skipped. I recommend at least skimming through these videos before continuing with mine. Now I will show several examples of modifying the game's assembly code. Remember in the video about address library, I removed the randomness effect on the NPC dodges. I did this by removing the GA instruction and replacing 2 bytes with hex 90, which means no operation, NOP. Now I will show more complex examples. NPCs can perform various actions such as fallback and circle. They do this at speed of 1, which corresponds to normal walking. To make fights more dynamic, the speed can be changed to 4. In these two places, a path for movement is created, and the last argument specifies the type of speed. This instruction sets the value of the R9 register to 1. Let's change it to 4 in both places. As I mentioned earlier, testing assembly changes is convenient in Cheat Engine. Use the right mouse button or the Enter key to modify the code. Change it to 4. Do the same in the other place. I will remove the sword and shield to prevent blocking, which slows down movement. As you can see, the NPC moves backward and sideways faster than usual. You can find a similar place for forward movement and modify it similarly. You can also try the value 0 to make movement even slower. The NPC will walk leisurely. While looking in Cheat Engine, you might have noticed that changing the instruction only altered the third byte. Likely, the first 2 bytes encode that this instruction moves a 32-bit constant into the lower part of the R9 register, and the next 4 bytes contain the value of this constant in little endian format. Since I'm changing the value from 1 to 4, only 1 byte changes. For practice, I suggest changing not only this byte, but the entire instruction. Let's use the website from previous videos. To get the instruction bytes, write it here. Don't forget to switch to 64-bit mode. As you can see, the bytes exactly match those you see in either. For convenience, you have been provided with a string literal and an array literal. I will show how to use them to modify the instruction. Copy the string literal and create a string view. The saveWrite function requires the destination address a pointer to the beginning of the string and its size. I will change the other instruction using the second method. Create an array of uint8s and fill it with data. Then pass a pointer to the beginning of the instruction a pointer to the beginning of the array, and its size. For convenience, I wrote a function that allows performing this operation in one line without creating auxiliary variables. An experienced modder might notice that the same effect of changing speed can be achieved by hooking the calls to these functions and substituting the arguments in the call to the original function. However, it seems simpler to call one saveWrite function than to create an entire hook. Moreover, a hook also generally won't avoid compatibility issues if two plugins attempt to modify this place. Let's test that everything works. Don't forget to use the right instruction, not the current one. It works. Now I'll tell you how I spent several hours on reverse engineering and ended up creating a mod with just 3 lines of code. I played Skyrim only twice, but the way arrows bounce off surfaces annoyed me. Look at how it appears. A few years later, after graduating from university and mastering reverse engineering, I decided to fix it. There is a function Projectile HandleHits, which calls the function Projectile AddImpact. The fourth argument is the negative velocity vector, which is then stored in ImpactData. Later, in the function missile projectile process bounce, the current velocity of the projectile is reflected relative to this negative velocity vector, causing the arrow to bounce back to the shooter. Instead of the negative velocity, the hit normal should be passed. Fortunately, at the time of calling the AddImpact function, the normal is already calculated by the game engine. It is extracted from the point collector and converted to Skyrim units at this point. The goal is to pass it as the fourth argument instead of the negative velocity. When hovering over a variable, either shows its location. For example, this and referB are in the R6 and RBX registers, while hit pause and normal are on the stack, indicated by RSP plus hex 68 and RSP plus hex 78. Since the difference is only 16 bytes, these two .3s are located consecutively on the stack. Negwell is also on the stack, Using the leer instruction, a pointer to the stack location of negwell is placed in the R9 register. There are two ways to pass the normal to the function. Change the pointer to point to the normal, or change the key.3 itself to contain the normal instead of negwell. The first method requires changing only one instruction, while the second requires a bit more. I will show both methods so you can repeat them and gain more experience. So let's change the pointer. The instruction currently looks like this. Note that the address is used relative to RVP, not RSP. This happens sometimes. You can also see how IDA conveniently recalculated the address and understood that this instruction takes the address of the key.3. To find out the actual offset of the address relative to RVP, hover over this variable. You will see its address. You can also double-click and IDA will show this tag. As you remember from the video about function signatures, auxiliary variables on the stack are located at addresses lower than the stack pointer at the time of the function call. To allocate the stack, the compiler subtracts a value from RSP. And to return it back, it adds same value. Therefore, the auxiliary variable negwell has a negative offset. The 5th, 6th, and subsequent arguments are located in the positive direction. You can observe this in the stack of the AddImpact function. Collidable, shape k, and hitHappened are passed through the stack. Here is collidable followed by the other two arguments. The 32 bytes before them are the shadow space, which I also mentioned. It can be considered a place for the first 4 parameters passed in the register, but the compiler can use it at its discretion. Now let's return to the instruction. Hover over the variable to find out its address. So, negwell is located in RBP-hex78, while the normal is in RSP plus hex78. Thus, the instruction should be like this. Check it in cheat engine. As you can see, the resulting instruction takes 5 bytes, whereas the old instruction takes only 4. This means that you have nowhere to put the last byte. If you agree, cheat engine will also override the following instruction to fit your code. Without hooks, you cannot write more bytes than you can clear. It's good that we have another method in mind, right? The value of the key.3 structure on the stack needs to be changed. As you can see, writing to this structure happens right before the function call. First, the velocity is taken and its sign is inverted. In assembly, it looks like this. The z coordinate is read into the XMM2 register and inverted. The same happens with the y coordinate in the XMM1 register and the x coordinate in the XMM0 register. These three instructions move values from the registers to the key.3 structure, i.e. the negwell variable. Here you can replace reading the velocity with reading the normal. Since we know that the normal is located at RSP plus hex 78, the instruction will look like this. Move SS is used because you're working with an XMM register, and the word PTR is used because you're moving one coordinate, i.e. float, i.e. for bytes. The white coordinate is located at RSP plus hex 70C, and the Z coordinate at RSP plus hex 80. All these instructions are unnecessary. Instead, you will write these three. It turned out to be 21 bytes. And you have 33 free bytes. That's enough. Better test this directly in the plugin. Fill the remaining space with knobs. Remember, you cannot add or remove bytes, only replace them. Otherwise, you will break all relative instruction offsets. It might have been irresponsible to change the argument for all types of projectiles. Perhaps somewhere else in the code, it's assumed that the negative velocity, not the normal, is passed. However, my not very extensive test showed that nothing broke. It works. If you are a perfectionist like me, you definitely won't like that the third instruction took more bytes, as well as the large number of knobs through which the processor will have to jump, like in a hurdle race. Nevertheless, this code already works, and you can leave it as is if it doesn't bother you. If it does, let's figure out how to make the code more compact and efficient. You can skip the next part and continue watching after it. So, hello my boring friends. First, let's deal with the third instruction. The bytes responsible for the offset are the last bytes of the instruction. The offset is a signed number, meaning the instruction can address both above and below RSP. Specifically, in the case of RSP, addressing below doesn't make sense, as it's the area of the color function. However, this instruction can use not only RSP as the base address. For example, if the function took actor state in the R6 register and accessed the fields of TestObjectRefer class by performing a static cast to actor beforehand, it would access in the negative direction. The range of a 1-byte number is from negative hex 80 to hex 70F. This means that you cannot just add hex 80 to RSP and therefore the instruction takes more bytes to fit the offset. However, this can be fixed by using another base address. I don't know if it's a coincidence or if the compiler did it on purpose, but this function has two kind of stack pointers, RSP and RBP. Some instructions use RSP as the base address and some use RBP, probably to reduce the length of instructions. Calculate the offset of the Z coordinate relative to RBP. I know three ways to do this. Look at the beginning of the function. Here, RBP is assigned RSP minus hex 78. Then, hex 178 is subtracted from RSP. So now RBP is hex 100 more than RSP. So, RSP plus hex 80 is the same as RBP minus hex 80. Minus hex 80 fits in 1 byte. The second way is to find instructions that address the stack through different base addresses. For example, negwell and hitpos. Looking at the stack, you can see that the address of hitpos is hex 20 bytes less than the address of negwell. Also, you can understand how these variables are accessed. Then literally solve the equation as in high school. It turned out the same. Replace the instruction. It became shorter because negative hex 80 fits in 1 byte. The third way is to set a breakpoint somewhere in the middle of the function and look at the values of RSP and RBP. This way, you will know the difference between them. I think you can do this yourself using cheat engine, so I won't show it. Let's deal with the large number of knobs. First, if you need to skip up to 9 bytes, you can use a long knob, so the processor executes them in fewer circles. The compiler usually does this before loops to align the instruction pointer. Here is the start of a loop. The instruction address ends in 0. Before this instruction, there is a 7-byte knob. Don't worry about what it says, the important thing is that it's a 7-byte knob. You can find the byte representations of these instructions online or in their relocation.h file. So instead of, say, 5 knobs, it's better to write one 5-byte knob. If you need its string representation, use the website. In our case, you need to write 16 bytes. A good way to do this with two knobs, one 9-byte long and one 7-byte long. However, I prefer GMP. Let me remind you how the offset is encoded in call and GMP. The address of the instruction after the current one is taken, and a signed number stored in the instruction is added to it. Short GMP instructions take 2 bytes. The first byte indicates the GMP instruction, and the second byte is the offset. You can experiment with instructions on the website. For example, to skip 4 bytes, you need to write 4 as the offset. In our case, we need to skip 14 bytes, as 2 bytes is used for the instruction. The remaining bytes should never be executed, so they can be left alone. However, for peace of mind, in case someone jumps into the middle of this area, you can fill them with knobs. This way, the processor fills the neg_val variable and then executes one GMP, skipping next 14 bytes. But if someone's hook or assembly insertion forces it to jump into the area modified by your plugin, at least there won't be a CTD due to attempting to execute part of an instruction. The use of GMP might seem excessive, but it has its advantages. My inner perfectionist would be 90% satisfied if there were two knobs. However, sometimes you need to skip a large section of code, such as a conditional operator or many instructions, and then using jump becomes necessary. Now you know how to calculate the offset and where to write it. Don't forget that you can use the website to check your hypothesis. Modifying assembly can be useful when using hooks. Let's consider an example where a hook cancels a bow shot if the player has low stamina. The code looks like this. I hooked the projectile launch call and return a null handle if the original function is not called. Check that everything works as intended. With plenty of stamina, the arrow is released. With low stamina, the arrow is not released. But if I use the legendary Phoenix bow, the game crashes. The reason is that I made the bow release multiple arrows, which causes the crash. Look at the function code. The loop runs as many times as the bow releases arrows. It initializes launch data, then launches the arrow. The function returns a handle, which is then used to find the arrow object. In this place, there is a check for a null handle. but in another there isn't. On the second iteration of the loop, the game accesses a null pointer to zero out some unknown field. To fix this, the corresponding instructions need to be removed. I couldn't find out what this field is or where it is used. Judging by its name, no one has found it and it's not used anywhere. So, it can be assumed that nothing will break if this field is not zeroed out. Let's try two options. The first option is to write only this instruction with a 7-byte knob. As a second option, I suggest practicing with GMP again. As you can see, the first launch variable is used only here, so the entire if statement can actually be cleared. That is, these instructions. You need to skip 21 bytes, 2 of which will be taken by the instruction, so the offset is 19 bytes. You already know the instruction code for jump with a 1-byte offset. Fill the rest with knobs. Check it. Now it doesn't crash and doesn't shoot. Note that it was quite irresponsible to simply cancel the projectile launch. For example, arrows are consumed. Even if this is intended, this code that triggers the Papyrus event should definitely not be executed. Although, who cares about Papyrus devs, right? Move to SKSE, guys. That's all for now. Today, you learned how to embed your assembly code into the game's code. Remember, you cannot change the total number of bytes. If there are unused bytes, write skipping GMP or a number of knobs. If the number of bytes you will clear is less than the number of bytes your assembly code occupies, you will need CombatBehaviorContextDodgeThreat, which I will cover in the next video. In it, I will explain how to use more advanced hooking method, including CombatBehavior. Have a nice day. Change Skyrim, play C++. See you in the next video.